check out this little video. I don't know, see if you can see anything wrong or amiss in this video. Okay, so that's a little weird. I suspect you could tell something was wrong. Those videos were run backwards, weren't they? How can you tell? What's so obvious about it? I mean, you could say, oh, well, the cars were putting themselves back together. Okay. Is there anything from a physics perspective that made it just obvious that those were backwards? And the answer is yes. What we observed in those videos is entropy decreasing. And whenever we observe entropy spontaneously decreasing, it's obvious that it's running in reverse. And we're going to come back to this idea again and again in this segment. The second law of thermodynamics says that the entropy of a closed system will always either increase or stay the same. And if we observe a situation that contradicts that, it's obvious. So, in some ways, the second law of thermodynamics is obvious, yet it's very, very subtle. The second law of thermodynamics is such an important law. I've heard it said that the second law of thermodynamics is the most important, least understood law in all of science. And I don't know if that's true or not, but I do think that it's poorly understood and very important. What is it? Part of why it's so poorly understood is that it can take on a lot of different faces. And it's not the mathematics behind it, though it exists. The mathematics behind it is much more in-depth than what we've been dealing with. And frankly, we're not really going to get into the mathematics of the second law of thermodynamics. We're going to state it as a general idea, and I'm going to kind of circle back and talk about how some of the results I've already presented are actually a result of the second law of thermodynamics. But mostly we're going to approach it from a qualitative, not a quantitative point of view. So, behold, a humble chicken egg. It is really a wonder of engineering, a chicken egg is, right? It's this shell around what can become a chicken embryo. Like, it's kind of crazy, right? And it's so tidy and organized, right? We've got the shell on the outside. We've got the egg, the white and the yolk on the inside. They're all separated. How about now? Okay, I have just broken my chicken egg. Can I ever put it back together? I can't, right? You didn't need physics class to know that. A broken egg is broken forever. Well, what does this have to do with the second law of thermodynamics? Well, we could talk about the entropy of this egg system, right? And entropy is a little bit of a hard thing to understand. It's really defined in sort of a strange mathematical way, but we can think of it as being the measure of a disorder of the system, as long as we accept that disorder here is not super well defined. Okay, so it's a measure of the disorder of the system. So I think we can agree that this egg is in a higher state of disorder now than it was when I brought it down here, right? So this egg's entropy has increased. And there's never any way that we can reverse that process. So this is a non-reversible process. I cannot decrease the entropy of the egg again by putting it back together, right? That's just not something that happens. And like, maybe you never spent any time to think about why, but why is it that time always moves in the direction where eggs break instead of in the direction where eggs get put back together? Well, it has to do with the second law of thermodynamics. So in this case, it's fairly easy to understand, the egg when it's whole is certainly a more organized, more orderly system than the egg when it's broken. So here we can just see the disorder has definitely increased. But often we use analogies like this to talk about entropy, and the entropy of this system did increase. But really, why entropy is such an interesting idea is because of its relation to energy. So let's think about the entropy of energy. Energy has low entropy or high entropy associated with it. So any highly organized form of energy has lower entropy, and heat, which is dispersed, has high entropy, right? So low entropy energy might be the chemical energy stored in a glucose molecule. Why do I say it has low entropy? Well, one way to think about it is it's very organized, it's compact, it's located within this single molecule. Another way to think about it, though, is it's very useful, right? I can eat that glucose and extract some energy to do something useful, right? And what happens to that energy after I eat it? Well, I'm doing stuff, I taught physics class, and now that chemical energy is gone. What form is it in? Thermal energy. Is it still useful? No, it's not. It's not useful at all, right? So that thermal energy that used to be chemical energy, it has much higher entropy when it's in the form of thermal energy spread out throughout this room than it did when it was chemical energy stored in a glucose molecule. And so this is the flow of energy. As energy changes forms, the entropy always increases. So, take this baseball here, right? Right now it's got a low amount of potential energy, and I have chemical energy stored inside of me. I can convert chemical energy into gravitational potential energy, like this. Amazing. Okay, so what happened? I just converted chemical energy into gravitational potential energy. The total amount of energy stayed the same, but the entropy of that energy increased. And now I can convert that gravitational energy into what? Kinetic energy, if I drop the ball, and then what? Well, I did work to break another egg. So we had gravitational potential energy. As it fell, it got converted into kinetic energy, and when it hit the egg, it did work to break the egg. The entropy of this system is much higher than the entropy of the system when I held the ball up here. You can just see it. And this is where entropy gets interesting, right? Entropy is interesting when we think about the disorder of the energy. Right? A lot of times we use these analogies of like the puzzle box, and when it's shooken up, then it has a lot of entropy, and then the puzzle all put together, it has low entropy. That is true. That is absolutely true. The puzzle is more organized when it's put together than when it is in the box. But entropy is really interesting when we start talking about not the disorder of a puzzle, but the disorder of energy. And if we think about the flow of energy all the way through this whole process to culminate here, it's a constant story of increasing entropy and decreasing usefulness of that energy. Recall that the energy I'm using to teach this class today was actually mass, right? E equals mc squared. It was literally mass in the center of the sun, something like 100,000 years ago. That's a very low entropy form for energy. Through nuclear processes, that mass got converted into energy, which traveled through space as electromagnetic energy, as light, right? As light, it traveled through space. It hit a plant. That plant converted it into chemical energy, which I ate, and then I did something with. Every step of the way, the usefulness of that energy decreases, and the heat of the universe increases. The thermal energy of the universe increases, I should say, right? So everything that we do in our lives is increasing the thermal energy of the universe. That's what we do. Humans are entropy-producing machines. We take in organized energy, and we expel disorganized energy. And that's the cost of keeping this highly organized human together. And what happens when I stop consuming high entropy energy? I die, right? And so, a lot of times I've read this argument where folks will make this argument where humans are highly organized machines. Any living thing is highly organized machines, right? If you think about it, I'm just a big ball of hydrogen, oxygen, carbon, and a little bit of other stuff, right? But yet I'm a very organized ball of hydrogen, carbon, and oxygen, right? I'm a low entropy ball of hydrogen, carbon, oxygen. And so I've heard the argument that the second law of thermodynamics can't be true because life itself is a contradiction, because a living being is more organized than the stuff that makes up the living being. And that's true. That part of it is true. But entropy of a closed system always increases, right? And so if I put myself in a closed system where I'm no longer taking in energy, well, guess what? I die, and my entropy increases very quickly, right? And so I have to be constantly consuming low entropy energy in order to keep my low entropy self together. Again, why is it that time always moves in that direction, right? Why is it that time moves in the direction where I always get older and not in the direction where I always get younger? So why does time move in the direction of increasing entropy and not the other way, right? I mean, you might have chuckled a little bit, but nobody was surprised when the egg broke. But how surprised would you be if the egg suddenly put itself back together? Right? That would blow your mind. I promise it would. Why is it that time always only moves in that one direction? I mean, from a human perspective, it just always does. But a good scientist should say, why? I mean, is there a reason it doesn't ever move the other direction? And so entropy provides a reason why. Okay, so now we're on to the second law of thermodynamics, right? The second law of thermodynamics, one of its forms, states that the entropy of any closed system must always increase. And so we see that time moves in a direction of increasing entropy, which is sort of the other side of the coin, right? If I say entropy always has to increase, well, then I'm talking about time. I'm implying time. And so, in effect, I'm saying, well, time must move in the direction of increasing entropy, which is very interesting, right? Okay, so now let's go look at this slide here real quick. So, higher entropy states are always more likely than lower entropy states. And that's part of why we can understand this, right? We can say, well, if I shake the box, if I've got a box of puzzle pieces, right, and it's not put together, and I give it a shake and I open the box up, it's going to be in a different arrangement than it was before I shook it. But that won't be obvious, right? You're not going to open it up and be like, oh, that piece was over here, right? It's going to look generally the same. You're going to open it up, you're going to say, it's about the same arrangement. It's all messed up. Close the lid, give it a shake. Each individual piece is in a different place, but now I look at it again, it's still just a messed up puzzle. How surprised would you be to give it a shake one time and open it up and the puzzle is put together? Oh, that would be mind-blowing. It would never happen, right? Why? Because there are so many, many, many high entropy states that look the same, but there's only one low entropy state where the puzzle is put together. Only one. How many different arrangements are there of puzzle pieces that are not put together? An infinite number, right? I mean, I just move one little piece, 1 millimeter. That is a new state. But take the put together puzzle piece, the puzzle that's all put together. I move one of those pieces 1 millimeter. I no longer have a puzzle that's completely put together. So there's only one low entropy together state. There are millions, billions, arguably infinite number of states for that puzzle that are not put together. So if I just take some random arrangement, well, it's not going to be put together, right? And if it is put together and it moves to some new random arrangement, guess what? It's going to be a not put together arrangement because there's only one put together arrangement. It's sort of a weird idea, but it's like we could say, hey, high entropy, low entropy, they're all equally likely. However, there's just way more high entropy states, and so that's actually what ends up happening. Kind of interesting, and a way to visualize that is, here is a low entropy organization of these particles, right? I move one particle, this one right here, and it's obvious that I moved one particle. You can pick it out right away. But what if I mess these up? I give my puzzle pieces a shake, and now we move to a higher entropy state. And now I move one particle. Well, do these two look different? No, they're the same basic arrangement, right? Yeah, one particle moved. And every semester I have to hunt for it again. Where is it? I believe it's this one right here. Yeah, so this guy right here moves from here to here, right? So you can find it. There's only, I don't know, what is this, 4 by... there's only, 48 dots here, right? So you can find the moving dot. But now imagine the particles in a room, right? There's gazillions of particles in this room. What if one of them moved from here to here? Is that a different state? Yes, it is. Does it look different? No, it doesn't. It looks exactly the same. Now imagine I came downstairs into my basement one time and all the air was in one corner of the room. That would be a very low entropy state and extremely unlikely to happen. I guess it's just as likely as the exact arrangement right now, where all the particles are spread around. It's just as likely to see them all up in one corner. But there's just a gazillion arrangements where the atoms are all spread around this room. And there's very, 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 very few arrangements where all the atoms are in one corner. So what happens? The atoms are spread around the room every single time. Okay, so increasing entropy, states with increased entropy are more likely to happen. And that's one of our statements of the second law of thermodynamics. Now, let's go here and let's look at some different statements of the second law of thermodynamics. Heat energy spontaneously flows from hot to cold. I've said that a number of times, but it actually, we can think about it as a consequence of the second law of thermodynamics. When two systems at different temperatures interact, heat energy is transferred spontaneously from the hotter to the colder, and never from the colder to the hotter. Okay, so heat will never spontaneously flow from cold to hot. That's a face of the second law of thermodynamics. Here's another one. Entropy considerations limit the possible efficiency of a heat engine. So that's where I've said you can never convert all of the heat into work. There's always some waste heat, right? In other words, we can never have a 100% efficient heat engine. What's our second law statement? It is not possible to make a heat engine that converts thermal energy into an equivalent amount of work. Okay. How about this one? It takes energy to move heat from a cold object to a warm object. That's very closely related to this first one, right? Let's see how the statement of the second law looks. It is not possible to make a heat pump that moves heat from cold to hot without external energy input. So you see how this guy's this first statement's sort of buddy, right? This says it will never spontaneously move from colder to hotter. But then this statement says, well, I have to input some energy in order to move thermal energy from cold to hot. And lastly, this is the one that I think is the most interesting. The entropy of an isolated system will never spontaneously decrease. And the statement of the second law here is that the time direction for which entropy of an isolated system increases is the future. Right? So we call the direction in which entropy increases the future. We call the other direction the past. And it turns out, as I've mentioned, right, I always have to be inputting energy into my body. I always have to be increasing the entropy of the universe. In order to do what? In order to make memories, right? So in order to remember what has happened and be alive and do this thing, whatever it is that I'm doing, I have to constantly be inputting energy. And that input of energy allows me to make memories, right? And so the future is the part of time that I can't remember. But that's because it takes increasing entropy in order to remember stuff. And time moves in the direction of increasing entropy. So, of course, I don't remember the future. Kind of crazy to think about. I'm going to post a reading written by the late, great Stephen Hawking on this topic. It's just a few paragraphs. I think you'll find it very interesting. Okay, so the second law of thermodynamics is, again, very important. It says that the entropy of a closed system always increases. And of course, the biggest closed system we can think of is the universe. So the entropy of the universe is constantly increasing. And so we can think about this as, we can sort of extrapolate outward and think, okay, well, what then is the ultimate fate of the universe? And it kind of depends on how much mass. There's sort of three options for the ultimate fate of the universe. It depends on how much mass there is in the universe. It could continue to expand forever. And right now, that expansion is increasing in speed, right? So it could continue to expand at an increasing rate for all time, in which case the entropy of the universe always continues to increase, the average temperature of the universe decreases, energy becomes less localized, more spread out, and eventually we have a very boring, very uniform, very low temperature universe with no life in it. Maybe, though, there's a little more mass, and that expansion just slowly decreases until at some point it just stopped, and that's it. I don't know what that future looks like. Apparently, entropy would remain constant at some point. So presumably life would no longer be able to function in a universe with constant entropy. But I don't know. I have a hard time wrapping my brain around that possible scenario. What about there's a lot of mass in the universe? The universe will continue to expand until at some point it stops and then begins to contract and gets smaller and smaller and smaller. Well, once that reversal happens, presumably we would live in a universe where entropy spontaneously decreased, where heat spontaneously flowed from cold to hot, where I remembered the future and not the past. I don't know. That's kind of weird to think about, but maybe that's where the universe is headed. And who knows? That's an open question in physics. So conservation of energy tells us that the total energy of the universe remains constant. But entropy considerations tell us that the usefulness of that energy is constantly decreasing. So these two ideas really work together to help us understand energy flow in our universe.